symmetric space of non-compact type. Okay, and one thing actually I forgot to told you that the Riemannian product of two Riemannian symmetric space of non-compact type is a Riemannian symmetric space of non-compact type. We can produce more example of Riemannian symmetric space of non-compact type. For instance, you can take product of SLNR mod S1 cross SLNC mod SUN like that. And one thing is this SUN comma 1 mod S of UN cross U1 is called complex hyperbolic space and it is denoted by CHN. Similarly, SPN comma 1 mod SPN cross SP1 is called quaternion hyperbolic space. Okay, so okay, so and also we have seen that to determine whether a Riemannian symmetric pair is effective or whether a Riemannian symmetric pair is of compact type, we need to have some knowledge about this center of the group. So for that reason, today's lecture will be really devoted to calculate center of some matrix groups which are familiar to all of you. So I will actually give a general procedure how to find the center of the group. Actually, I don't know whether you will be able to find this thing in book or not, but actually I have done those things for myself. For actually, let us start then. So let us pose the problem in much more general setup. So let S is subset of MNC or MNR or MNS. Okay, where H is the set of all quaternions. I define this Z of S. This is really A belongs to S, so that AB is equal to BA for all B belongs to S. Now you took a look at this lambda S. Okay, so what is ZS? ZS is the precise the element of S that commutes with every element of S. Okay, so if S is the Lie group, that this is precisely the center of the group. Now I will, by abuse of language, I will also call that center of S. But S may not be a group, but I will call this center of S. Similarly, I will define lambda S is equal to really A belongs to S. So that A is equal to lambda Y for some lambda belongs to K. Okay, where K is equal to either R or C or H. That is basically the set of all diagonal elements in S. And lambda, if I am taking a subset of MNC, I will take K to be C. If I am taking S subset of MNH, I will take K to be H. So the examples which we will see that our aim. Okay, so so the examples which we will look at, for those examples, what we will get? We will get the ZS subset of lambdas. Okay. So our task is to show ZS subset of lambdas for suitable S. If you can prove that this fact that ZS subset of lambda S, then after that everything is easy. Okay, so this is our this should be our goal. Now some known results which you probably know. So if you look at this thing Z of MNC, this is really lambda I. So that lambda belongs to C. And since Z of MNR is equal to really lambda I, so that lambda belongs to R. Okay. I am sure that all of you know this group, because what you would take, suppose A belongs to ZMNC, A belongs to center, then AB is equal to BA for all B belongs to MNC. Then instead of B, you just choose this EIJ is equal to EIJ then you will get this result. These are elementary exercises. Now, as this GLNC is dense in MNC and the matrix multiplication is continuous, is continuous. This implies that if A belongs to something like Z of GLNC, then A will belongs to Z of MNC. By continuity, it can be, you can easily check that this implies A is equal to lambda I for lambda belongs to C, but therefore you can conclude that thus Z of GLNC is equal to really A belongs to A belongs to, this is really lambda I, so the lambda not equal to 0 and lambda belongs to C, that is lambda belongs to system. Similarly, if okay, so similarly GLNR is dense in MNR, Z of MNR or Z of GLNR, so lambda I, so that lambda belongs to R star. These are some results you know. And another fact, interesting fact is something like that. Any linear operator in CN is really can be written as linear combination of 4 unitary operators. So this result is slightly non-trivial and it requires little bit of operator algebra to prove it. So actually the proof which I know that uses operator algebra. So then if A belongs to ZUN, from this fact, suppose A belongs to ZUN, so that will implies A belongs to Z of MNC. So that means A is equal to really lambda I for some lambda not equal to 0. After that, for some lambda belongs to C. After that, using the fact that A belongs to UN, so
You know, I missed something.
okay, so your sound voice, you're too loud. Okay, for me. Okay, tell me.
Too loud.
Yeah, but I don't know. Now it is okay.
See, A in Z of UN, then how is A is in Z of MNC?
Okay, so A can suppose A belongs to Z of UN, right? Okay, I am explaining this thing. Okay, so reason. Okay, I am writing this. Did you get now? So let A belongs to Z of UN. Let B belongs to MNC. So then B can be written as some lambda 1 U1 plus lambda 2 U2 plus lambda 3 U3 plus lambda 4 U4. U4 UI belongs to UN, right? Now AB, therefore AB is equal to BA, right? Do you get now?
Okay,
So
linear
AB is equal.
combination. Yeah, once you write it as a linear combination, then only scalars are left. So,
Yeah, so that is the thing. So this is
no,
the
just
thing.
you go back to the statement. I think the reason I got confused is you said is A, if A is in Z of UN, then A belongs to Z of UN. Because that A equal to lambda for some values. So To show this, you are using the fact that it can be written as a linear combination of four unitary operators.
Yes, yes, yes.
Okay.
So we use fact here. This is the thing actually. Okay, so there are other suggestions also. Let us keep this page somewhere. Let me use this thing. Okay. This one. So other suggestions. There is something. I will do these things in a different way. Okay, as I said that I will do everything in a general way. As this thing GLNC UN SUN. So I am just asked irreducibly on CUN. On CN. There is something called source lemma. By source lemma, by using this source lemma, so one can show that Z of GLNC is really lambda I, so that lambda belongs to C star, T star, and Z of UN is equal to you have to, what is source lemma? You just check after this lecture. So, but and these are the some ways. Okay. So actually, source lemma says that if some if some, since this UN acts irreducible on Cn, if some operator will commute with all these UN, that has to be scalar times identity. Okay. So this directly follows from that. But there are some obstruction to use source lemma, because, for instance, if some group consists of only real matrices, you cannot really use source lemma, because here one fact you are using that thing is um, C is algebraically closed. Okay. So this method is not that much robust enough to accommodate all the group. And also these things, that apart from these two things, you need some higher means some difficult, some non-trivial result to prove these things. So okay, but however, there are some ideas are there. We will use those ideas to really to find the center of the group. Okay, so first thing is, recall I have told you a proposition. Okay, so let V be a vector space over K. Where this K is equal to really R or C. So let A comma B belongs to endomorphism of V over K. Suppose this AB is equal to BA. Then A preserves null space of B, eigenspace of B, and image of B. And image of B. So I have told you this proposition before also, and this I like this proposition very much because it is useful. Okay, so we will use some discussion here. So let again let P be a vector space over K. Okay, where K is R or C. So let A comma B belongs to endomorphism of B over K, so that AB is equal to EB. Suppose S is equal to really B1, B2, Bn, be a basis of V over K. Okay, such that this thing B of Vi is equal to lambda I Vi. This is really I1 less than equal to I less than equal to n, and lambda I not equal to lambda j. So that means B is
So
diagonal.
you are assuming V is diagonalizable.
By diagonal and with for distinct eigenvalues. So this means B is okay. S is an eigenbasis or diagonalizable. S is an eigenbasis of B with distinct eigenvalues. So I am assuming this. Now let's look at this n lambda I. This is kernel of P minus lambda II. Okay, so since this is really see, B has distinct eigenvalues, so this n lambda is one dimensional, and this is really nothing but span of Vi. This is really one less than equal to n because the eigenvalues are distinct. Now as AB is equal to BA, so that implies that A of n lambda I is contained inside n lambda I by previous proposition. Okay. So that means what? That means A of Vi is equal to really mu I of Pi because n lambda is spanned by just Pi. So this mu I should belongs to where? K. Okay, so this means A is also diagonalizable. So, thus A is diagonalizable with respect to basis S. So, but this mu I am not saying that A has distinct eigenvalues. I am not saying that. I'm just saying that A is diagonalizable. But B has distinct eigenvalues. I am assuming. So let me repeat this once more. So I am taking this B is a vector space over K, where K is either R or C. Let A comma B be two linear operator on B, so that AB is equal to BA. Suppose B is diagonalizable with distinct eigenvalues, or B has a eigenbasis with distinct eigenvalues. Then if A commutes with B, then I am getting this A Vi is equal to mu I Vi. That means A is diagonalizable. Okay, so now we will apply this thing. So application. Let us first start from a non-trivial example. So let us do it for z of U. Okay. So let A belongs to z of U. Okay. So let B1, I choose the first element B1 is equal to really lambda 1, lambda 2, lambda n. This is the diagonal matrix with lambda, okay, mod lambda I is equal to 1 and lambda I not equal to lambda 3. So this is possible to choose different elements because S1 is real uncountable. So you have to just pick n points, different points. That is the thing. So clearly this B1 belongs to UN. Now as AB1 is equal to really B1A. So that will give you what A is equal to I am using this previous discussion. That will give you A of EI. Here the basis is the standard basis. Here basis is the standard basis. AEI is equal to really mu I UI. This is by previous discussion. 1 less than equal to I less than equal to. This is by previous discussion. Okay.
Lambda
Yes.
lambda is the solution of lambda to the power n equal to 1.
Lambda, no, I am not UN, just unitary matrix. Unitary matrix determinant may be determinant is not necessary. Do you get it?
If b1 equal to diagonal of lambda 1 lambda to lambda n, then you said
Where
b1 belongs where?
UN.
Oh,
Because
lambda.
mod
Okay,
of lambda I is equal to 1.
oh, I thought this is mod of lambda 1 equal to 1. Sorry.
No, lambda I.
That's okay.
Sorry, that's okay, right?
Okay.
So B1 belongs to UN. Since as A B1 is equal to B1A and B1 has distinct eigenvalue, so therefore AEI is equal to mu UI. My previous discussion. Okay. So now this implies A is equal to really mu1 0 mu2. So let us write A is equal to really mu1 0 0 0 mu2 and this 0 mu1. So diagonal element, this is really mu1 mu2 mu. Now this mu I belongs to where? C. Mu I belongs to, because I am taking everything is inside C to the parent. Now okay, I have to what I have to show? This mu1 is equal to mu2 is equal to mu1. I have to show that it is scalar matrix. So I have to choose this mu1 equal to mu2 is equal to mu1. Suppose I want to show mu1 is equal to mu2. Okay. So mu1 is equal to mu2. So what is the strategy? So I will choose some matrix B2 in such a way that if I will apply this thing AB2 is equal to B2A, so that will give me this mu1 is equal to mu2. Okay. So this is my strategy. Now what is mu1? Mu1 is the first diagonal element of A and mu2 is the second diagonal element of A. So the natural thing which comes to you, if you think for a moment, the most natural thing will come to your thing is this B2 is something like 0 1 1 0 0 0 0 and 0 0 1. Okay. And everything is 0 0. Everything is identity matrix here. This one. So this is 0. So this is the matrix. This B2 is the elementary matrix which really formulates the row 1 and row 2. So for precisely what is B2 of E1? B2 of E1 is equal to really E2 and B2 of E2 is equal to E1. So now AB2 is equal to B2A. Okay, this clearly this belongs to UN because this belongs to ON and ON is a subset of UN. ON and that is a subset of UN. Okay, so AB2 is equal to B2A. So this implies A B2U1. Oh, sorry, B2U1, B2E2 is equal to U1. Sorry, I just wanted to write something. B2 of EI is equal to EI for I greater than equal to 3. Okay, that is the thing. So, and clearly B2 belongs to ON and this is subset of it. Okay, so now AB2 is equal to B2A. That means AB2 of E1 is equal to B2A of E1. So that will give you a B2 of E1 is E2 and B2 A of E1 is equal to mu1 E1. You remember if this was the matrix. So A E1 is equal to mu1 E1. So this is equal to mu1 B2 of E1. Now A E2 is really mu2 of E2 and this is really mu1 B2 of E1 is really B2 of E1 is equal to E2. So mu2. So this implies mu2 is equal to mu1. So this is as I have done for this So this mu2 is equal to mu1. What I will choose the matrix B2 is. But for any general J and K, suppose you want to show that mu J is equal to mu K. Okay, so you have to really take the matrix, permutation matrix, which really interchanges rho J and rho K. So let us write those things because we will use those things later. Okay, so now you understand the whole idea, I think. So fix J comma K, okay, with 1 less than equal to J, K comma N. So define Bj comma K by Ej is really Ek, and Bj comma K, Ek is really Ej, and this thing Bj comma K, Ei is equal to Ei if I not equal to J and I not equal to K. Okay, so then clearly this Bj comma K belongs to where O N, and that is the subset of SU. Okay, sorry, not SUN, sorry, OUN, sorry, UN. And so A BJK, large A belongs to the center, is equal to BJ comma K A. This implies A B J comma K EJ is equal to BJ comma K A EJ. And this is really what? This is BJ comma K A EJ is really mu J is A, and mu J Bj comma K is A. So this is really A, and Bj comma K is A is what? This is Ek. Now this is really mu K Ek is equal to really mu J Ek, and this implies mu J is equal to mu K. Hence we get this, since J and K are, you can vary J and K, and you get mu1 is equal to mu2 is equal to mu3. This is really mu n. Say mu say. Okay. Hence A is equal to really mu I, and up for some mu belongs to C, and after that there is nothing. Thus Z of UN is really, since A belongs to UN, mod of mu has to be 1. Z of UN is equal to really mu I, so that mod mu is equal to 1. So this is this will be the general idea for all the group. So let us quickly recap what we have done. First, you take A belongs to ZUN. First element you should choose an element B1 which has really distinct eigenvalues, and that is diagonal. And such type of elements are called regular elements. Okay. Now for A B1 is equal to B1A, that will give you A is equal to some diagonal matrix mu1 mu2 mu n, and then you choose some Bj comma K. Okay, so that you will get this mu J is equal to mu K, and then therefore you can conclude that A is equal to of the form mu I. Then there is nothing after that. Okay, so this is the first case, first example. Let us do the second example. So that G is equal to really SUN. So let A belong. Tapendu, is it clear?
Yes, Manoj. Yes.
Rajesh Bhaiya? It seems Rajesh Bhaiya is not there. Let B1 is equal to B1 is equal to you have to apply the same strategy. Now lambda to lambda n. with lambda is not equal to lambda is mod is equal to 1 and lambda I not equal to lambda j, and here there is a condition lambda 1 lambda 2 lambda n it should be 1 because clearly b1 belongs to SUN. Okay. But you can ask that whether such type of elements exist in B1 or not. Can you? It is possible to choose such types of element in SUN where these diagonal elements are different, and this is possible because in fact there are infinitely many ways, but I am just giving a simple way. So for instance, choose sorry, choose this 0 less than equal to theta 1 less than theta 2, theta n minus 1 less than pi, so that this theta, which is nothing but theta 1 plus theta 2 plus theta n minus 1, is less than also pi. Okay. So this is my picture. This is my picture. So this is my say theta 1. This is my theta 2. Similarly, this is my theta 3. But sum of this theta 1 to theta n minus 1, that is really less. This is my say theta. So this is my theta. This theta is also less than pi. And if you look at this minus theta, that minus theta is really here. This is really minus theta. Minus theta. Now clearly, by this choice, so clearly this, okay, by this choice we can really e to the power I theta, e to the power minus I theta is not equal to really e to the power I theta I or I theta j, sorry, or any j 1 less than equal to n minus 1. If you look at this thing, let b1 is equal to, then one can choose, one can take this b1 is equal to really e to the power I theta 1, e to the power I theta 2, e to the power I theta n minus 1, and this is really it minus e to the power I theta. So this is really sorry. So, okay. So this is actually, there is something here actually. By writing this, okay. So b1 one can choose that. So this is so as a b1 is equal to really b1a. So b1 has different eigenvalue. Therefore, this implies a ei is equal to really mu I ei. Right? So I is equal to really 1 to n. That implies a is equal to really mu 1, mu 2, okay, mu n. Diagonal of this thing. Now I have to really choose b2 in such a way that ab2 is equal to b2a will imply that this is really mu1 is equal to mu. Let us look the thing whether this element which we have taken for un case, does it work? Okay. So clearly if you take this b2 element, then that will give you that mu1 is equal to mu2, but there is a problem here. This b2, if you look at this determinant of b2, this is really minus of 1. So determinant of b2 is minus 1. So this element will not work. So but if you modify this element a little bit, then it will work. What you do, instead of 1, you take here minus 1. That will do the job. So This B2 will not do that, but here if you took -1, that will do that. Similarly, but I don't want, I am not interested in that. I'm interested in this example because this is more general. Bj comma k is determinant of bj comma k is -1. Why? Determinant of bj comma k is really -1 because it corresponds to a odd transposition. So therefore it is a permutation matrix, and since it is corresponds to a odd transposition, therefore its determinant is -1. Okay, so I have to change this thing. So for actually what I'm saying that you take this as C1 actually. So that will be, I'm just changing this notation a little bit. C1, this is actually C1. Sorry, I am changing this notation C1. Okay. So this SC1 is good. Okay. Now I want to change this for fixed j comma k with 1 less than equal to j, k less than equal to n. Let Cj comma k be the matrix. Cj comma Ej should be Ek, and Cj comma k Ek is really minus Ej, and Cj comma k Ei is equal to really Ei for 1 less than equal to I less than equal to n. For sorry, for I not equal to j and I not equal to k. So a Cj comma k is equal to Cj comma ka. This implies a Cj comma k. Let us take Ej. Okay, let us take Ek. Okay, let us say Ek is equal to Cj comma k Ea. You can work with Ej also. There is nothing. So a Cj comma k Ek is equal to minus Ej. Right? So Cj comma k Aek is equal to what? Mu k Ek, right? So this is really minus A is, and C mu k Cj comma k Ek. So Cj comma k Ek is equal to, okay. So this minus of A is equal to what? Mu j is mu k, and Cj comma k Ek is equal to minus of what? Minus of Ej. So from here you get this implying mu k is equal to mu j. Okay. Hence we get A is equal to really, hence we get this mu1 is equal to mu2 is equal to mu n. Thus A is equal to really mu I for some mu belongs to C, and then you get this thing A is equal to lambda I, so that lambda to the, sorry, this z of sun. Now after that everything is in lambda I, so that lambda to the power n is equal to. So this is for un, and okay, this un. Now let us look at the same example for GLNR or GLNC. So I am just writing the matrices here. First take B1 is equal to something like diagonal of 2, 3 up to 2 n plus 1, and this has distinct eigenvalues. So now AB1 is equal to, okay, now you will take this thing, B2 is equal to, okay, now Bj comma k. So if you will use this fact that AB1 is equal to B1a, that okay. So let A. So first consider GLNR. So it's going to be GLNR. But A belongs to GLNR. Z of GLNR. So AB1 is equal to B1A. That will give you this A is equal to diagonal of this mu1, mu2, mu k. Now where with mu I belongs to R. This is an important thing. Here this mu I will belong to R because this element is diagonalizable over R. With mu I belongs to R. Now choose Bj comma k.
This should
Yes.
be diagonal mu1, mu2, mu n, right?
Mu n. Thanks. Yes. Choose Bjk as in the case of SUN, as the case of UN. Then so ABJ comma K, BJ comma KA will give you what? Mu J is equal to mu K, and therefore A is equal to really lambda I, and thus lambda belongs to R. Thus what Z of GLNR is, you can get this. You can get whatever you want. Lambda I, so that lambda belongs to R star. For GLNC, you exactly take the same set of matrices to that one. For GLNC, so or you can also include this case MNC or MNR. Okay. Take exactly the same set of matrices as that of GLNR. Now 5 is this is interesting SLNR. So let A belongs to really Z of SLNR. So first you have to choose a element which has distinct eigenvalue. Take B1 is equal to really 2 diagonal of 2, 3, 4 up to n plus 1 by 1 by n plus 1. I am so this is belongs to SLNR. Now after that you will conclude that A is a diagonal matrix AB1 is equal to B1 and take okay, so here determinant is 1 and the matrices which you have taken for SUN case, this determinant Cj comma k is really determinant of 1 and these are all real matrices. So take Cjk as in the case of SUN, then AB1 is equal to B1A and ACJ comma K. Yes.
How this B1 belongs to SLN? Multiplication.
Oh, sorry. Okay, sorry. Okay, thanks that you are. It seems that offender is listening carefully. Okay. Sorry. Actually, take B1 is equal to really diagonal of 2, 3 up to n plus 1. And this 1 by 2 into 3 into n plus 1. Okay, that is, now this is fine, right? Tapendra, now it is fine, right?
Yeah.
This A is Cjk is equal to Cjk This is A is equal to lambda I, you will get. There is nothing. So Manali, is this clear? Or Santanu, Manali, who is there? I don't know.
Yes, Monada, it is clear.
Okay. So now for SLNC. For an SLNC, you have to just since SLN are sits inside SLN, take take the same matrix as that of SLN. Same matrices. Same matrices as that of SLN NR. And you here actually you will get that. So first you will get the A is equal to lambda I, then there is nothing to prove. After that, just you have to use this factor determinant of SL. That matrix is 1. So thus we get what Z of SLNC is really plus minus identity if n is even, and identity is really n is odd. And this is same thing as really Z of SLN. These are now there is an interesting example which we will do now. 5, 6, 7 case. SO2M. And for M is equal to 1, actually. So you know that Z of SO2 is abelian. So Z of SO2 is really SO2. We will do this for M greater than equal to 1. Okay. For before that, I need to little bit discuss something little bit. So little bit of discussion. So let R theta is equal to really cos theta sin theta minus sin theta cos theta. This is the rotation matrix. And theta I will take from 0 to 2 pi always. Now, if you look at this R theta into 1 minus I, so you will get this thing cos theta minus sin theta cos theta. Okay. This is really 1 minus I. Okay, so this is really cos theta plus I sin theta and sin theta minus I cos theta. Now, if you can really write that thing e to the power I theta into 1 minus I. Okay, so let us do that. This is the cos theta plus I sin theta. This is really minus of I sin theta plus minus I if I will come out. So this is let us skip that. So really this is really e to the power I theta into 1 minus I. So what I am getting really R theta if I U1 plus I U1 minus IE2 minus IE2. This is really e to the power I theta into U1 minus IE2. So, but U1 minus IE2 doesn't have norm 1. So, to make it norm 1, I am really dividing by root 2. So, then taking conjugate, what we'll get? Conjugate, in both sides we get this thing. R theta 1 by root 2 U1 plus IE2 e to the power minus I theta U1 plus IE root 2 by root 2. Okay, so this is the thing you should remember. If R theta, I am taking this 1 by root 2 U1 minus I root 2. So I will get this thing 1 by e to the power I theta and something like that. Something this thing. Basically, R theta has eigen values e to the power I theta and e to the power minus I theta, and these are the corresponding eigenvectors. Okay, so now I discuss the case 5, 6, 7. This is the 7th example. So let us see SO2M. For M is equal to 1, Z of SO2 is equal to SO2. You know, this is for M. So assume that M is greater than equal to 2. Now let A belongs to really Z of SO2. The first element which we were choosing, that something is a diagonal element, diagonal matrix, something lambda 1, lambda 2, lambda m, lambda 2m, we were choosing, and this lambdas are different. But since we are, this B1 should belong to SO2m, if I am choosing a diagonal matrix inside SO2m, this lambda I has to really plus minus 1. Okay. So since lambda I has to plus minus 1, so it is inevitable that there will be more ones and more minus ones. So it will, so number of 1 will be more than 1, number of minus 1 will be more than 1. That is a problematic thing. So for that reason, I will choose this thing as like B1 is equal to really R theta 1. This is 2 by 2 block. Okay. R theta 2 and R theta m. Okay. So this is just in the diagonal entries are constituted of 2 by 2 block, and this is just R theta 1, R theta 2 and R theta m. So I will choose this theta 1, theta 2, theta m latter. Basically, I will choose theta 1, theta 2, theta m latter, so that this eigenvalues of B1 will be different. So this is really, this is all are 0, right? This is really, you can write this thing as diagonal of R theta 1, R theta 2 and R theta m, with understanding that these are really 2 cross 2 blocks. Okay. Now let V1 Pi really 1 by root 2. Okay, so let us write Vj here, because 1 by root 2 e to the power 2j minus 1 minus e to minus I e to the power 2j minus I e to 2j, j is equal to 1 to m. Then Vj bar is really 1 by root 2 e to the power 2j minus 1 plus I into e to 2j. So then V1 Vj is equal to really e to the power, by this choice, e to the power I theta j Vj. Okay, and B1 Vj bar is equal to minus I theta j Vj. Because of I am doing this, because of I am getting this from this thing. Okay, so this happens for j is equal to 1 to m. Now I will choose my theta j.
Muna, the last one is Vj bar, right?
Yeah, Vj bar. Thanks. Okay. So choose theta 1, choose theta 1, theta 2, theta m in such a way that e to the power I theta j is not equal to e to the power I theta k if 1 less than j not equal to k less than equal to m, and e to the power I theta j is not equal to e to the power minus I theta k if 1 less than equal to j k less than equal to m. So that means this eigenvalues of this thing are distinct. So this means eigenvalues of B1 are distinct. Values of B1 are distinct. Simply this means. And this is always possible. For instance, you can choose this. Okay, this is always possible. Theta 1, theta 2, theta k in the upper half, theta m, right? Theta m in the upper half plane. And so this is always possible. Actually, you can Okay, so now, okay, so now this now a b1 is equal to really b1a. So what you will get here? This you will get what? That means a of p is a. Okay, so I have to really write clearly this thing b1 bar, b2 bar, and bm bar. So is an eigenbasis of p1 with in C with distinct eigenvalues. Okay, I am writing this. Now a b1 is equal to b1a. This will give you me a of bi. This is really mu I bi. By that discussion which I am saying. Now since a belongs to really SO2m, this mod of mu I has to be 1. Okay. So that means this is really mu e to the power I. So let us write it j here. This is really e to the power I alpha j. So alpha is so j is equal to really 1 less than equal to j less than equal to m. And a b j bar is equal to really e minus e I j b j bar. Okay. So this is really what alpha j belongs to 0 to 2. Okay. So now this is with respect to this basis, but I want everything in terms of the standard basis. So thus a will be this thing r alpha 1, r alpha 2, this is r alpha. In terms of standard basis, this will be this. So if you will convert back, then you will get this. Okay, so now what is our task? Our task is to show alpha 1 is equal to alpha 2 and alpha 2 is equal to alpha 3 and up to alpha n. So to show this alpha 1 as, how do you show this alpha 1 is equal to alpha 2? So you apply that the same process method which you have done in the case of so-called UN. So suppose I am let B12 the matrix. This is really, see the thing, I have to show this alpha 1 is equal to alpha 2. That is, since alpha j belongs to 0 to 2 pi, suffices to show that r alpha 1 is equal to r alpha 2. Okay. And you can think these elements are entries. Okay. But the entries are 2 cross 2 blocks. So we have to show that r alpha 1 alpha 2. So this is the matrix we have to take. 0 I 0, and only this is the thing. This is a 2 cross 2 block, and this is really 0 0 0 identity. This is the just permutation matrix which really permutes row 1 and row 2. And this I is a 2 cross 2 block, is a 2 cross 2 block, and everything is, you know what it is. Okay. So a b1 2 is equal to b1 comma 2a, multiply blockwise. This is, you will get this thing r. If you multiply blockwise, you will get this r alpha 1 is equal to r alpha 2. So this will give you alpha 1 is equal to alpha 2. Okay. So similar alpha 1 or alpha 2, but I have done this for 1 and 2, but you can choose for any j and k. Similarly, oh, one thing I just forgot to verify. this thing B12 corresponds to really O2M. This is clear, but you have to show that this determinant of B1 comma 2 has determinant 1. So that is easy. Okay, so okay, so clearly this B2 now determinant of B12 is what? Since this thing is my identity determinant of this thing 0 I is 0. This I is a 2 cross 2 matrix, and this is really determinant of 0 minus identity. I am using this fact that if I am using that fact, this fact, if U comma V W Z commute with each other, so determinant of U V W Z is really determinant of U Z minus W. Okay, so this fact I am using. So determinant of 0 minus I, this is determinant of minus I, but I is a 2 cross 2 matrix, so this is really 1. So hence this B12 belongs to SO2M. So hence this B12 is really belongs to SO2. Now similarly, choosing suitable matrices B, J, comma K with 1 less than equal to J, comma K less than equal to M in SO2M, we get this thing alpha J is equal to really alpha K. Okay, so hence we get, oh my god, hence we get this thing A is equal to really R alpha 0. So let us write this diagonal of R alpha. Now I have to what I have to show this A is equal to identity or minus identity, right? That is the result. So observe. So let F is equal to really 0 1 1 0. So and determinant this A belongs to F. This belongs to O2, and determinant of F is really minus 1. Now F is equal to okay. R alpha F is equal to F R alpha. This is if and only if cos alpha, sin alpha, cos alpha 0 1 1 0. This is equal to 0 1 1 0. Cos alpha minus sin alpha. Sin alpha, this is cos alpha. Okay. Now the thing is, this is really a elementary matrix, okay, which interchanges the two rows basically, but I am not multiplying from right, so it will really interchange the columns. So this is really minus sin alpha, cos alpha, sin alpha, and this is really interchange the rows. This sin alpha, cos alpha minus sin alpha. And look at this thing. So this implies that minus sin alpha is equal to sin alpha. This if and only if the sin alpha is equal to 0. Therefore, cos alpha is equal to really either 1 or minus 1. So this implies R alpha is either identity or R alpha is equal to minus identity. Now I will use this F to construct this thing. Okay, so observe that determinant of is equal to minus 1. So let final step. Let B3, okay, BJK was there, B12. Okay. Let B3 is B2, okay. Let B2 is equal to really F 0, 0, F. Okay. And rest of the things are identity. 0, 0, identity. Identity is a 2m minus 4, and this is really 2m minus 4 and 2m minus 4. So this is the thing. Okay. Now since I am taking two f's here, clearly determinant of B2 is equal to 1 because I am taking two f's. And here actually I am also using this fact that m is greater than equal to 2. Okay. This belongs to O2m and the determinant of B2 is equal to 1. Now AB2 is equal to B2A. So let us write this. What is A? This is the diagonal of R alpha, R alpha, R alpha, and B2. Okay, so this is B2. And what is B2? This is diagonal of F, 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 identity, and everything is a 2 cross 2 matrix here. This is a real diagonal of F, identity. So this is the real diagonal of R alpha, R alpha, R alpha. It will just multiply like the usual way. So this is really diagonal of R alpha F, R alpha F, and this is really R alpha. And rest of the things are R alpha. So diagonal of F R alpha, F R alpha, and this is really R alpha, R alpha. Now R alpha F is equal to thus is equal to F R alpha, and this implies R alpha is equal to either identity or R alpha is equal to minus identity. Hence we get this thing. So if A R alpha is equal to identity, then A will get identity, or A is equal to minus identity. If R alpha is equal to minus identity. So is this clear, Anway? Manojda?
Yeah, it's clear.
See, why are you
Manojda,
doing for only two? Why are you doing for only two? Two F. You can take as many M Fs, right?
because I need only one thing. I have to just conclude this R alpha is equal to identity.
Yes.
So I just only do. You can do for as many as you like, but I need this only R alpha conclude the identity. Therefore, I am taking two F's.
If you take only one, if you take only, then you don't have determinant one. Okay.
Okay. So now let us do the second case, SO2m plus 1.
So the center is basically n-fold product of SO2, right? No, sorry. Sorry. Plus minus identity.
So yeah. So 8. So let G is equal to really SO2m plus 1. Okay, so let us actually SO2m minus 1 plus 1. This is really any elements of SO2m plus 1. Okay, so 3. Okay, SO2m plus 1. Okay, let us see. This is the odd degree. Okay, so let B1 tilde, I will choose this thing. B1 0 0 1. Okay, so let us write first. Let A belongs to center of SO2m plus. So let B1 is equal to really B1 tilde is equal to B1 0 0 1, where B1 as in the case of SO2m Okay, but the thing is, here actually one is another eigenvalue. So with this thing, I take this B1 is as in the case of S1 and I will take another more condition because one is another eigenvalue, so that e to the power I theta j not equal to 1 for j is this thing is 1 less than equal to n. So that will automatically imply that e to the power minus I theta j not equal to 1. Okay, so this has a different eigenvalue. So you conclude this thing a b1 tilde is equal to b1 tilde a. So that will give you, okay, a bj is equal to really e to the power I alpha j bj, okay, and a bj bar is equal to e to the power minus I alpha j bj. That will give you, now here actually you will get another basis vector e to the power 2m plus 1. This really something like mu e to the power 2m plus 1. Sorry, mu e of 2 e2m plus 1 you will get. So this is really j is equal to really 1 to m. Okay, where this bj, okay, bj bar are as in the case of SO2m plus 1, SO2m. Okay, now observe that this thing mu j, okay, so one thing, see this eigenvalues occurs in pair, e to the power I alpha j, e to the power minus I alpha j occurs in pair, and since determinant has 1, so it has to be really 1. This a e n 2m plus 1 is equal to e to the e to m. So this will get this thing. Okay, now okay, so this is the thing. Thus I will get what? Thus we get this thing. Okay, let us write. Thus we get this thing. A will be, you will get this thing R alpha 1, R alpha 2, R alpha m. At last coordinate is really 1. Diagonal of this thing 0. Yeah, so this is really 0. This thing will be 1. Okay. Now I have to conclude this first. This alpha 1 equal to alpha 2 is equal to alpha m. I have to conclude that. For that reason, choose bjk tilde. Okay, so that is really b j comma k and 1, where bj comma k is an where bj comma k as in the case of SO2m. Okay. So hence, okay, now if you look at this thing a bj k tilde into bj comma k tilde a, so there from there you will get this a is equal to r alpha 1. So yeah, let us write this diagonal of r alpha 1. This r alpha is a 2 cross 2 matrices and 1 is the 1 cross 1 cross 1 matrix. These are 2 cross 2 matrices. Okay, so yeah, I will get that. Now I have to conclude this first. R alpha is equal to real identity, or R alpha is equal to minus identity. So for that reason, I have to what? I have to choose. I have to. So I will choose this B2 tilde. So the natural thing is really you should choose this diagonal of F2, then F2, okay, and rest of the things are identity. But okay, so this is the thing. But when the moment I choose 2f2, then you have to assume that dimension of the space, okay, is greater than equal to really 4. My sorry, 2m plus 1. This 2m plus 1 has to be greater than equal to 5. You have to assume because we are accommodating 2f2 there. So that will exclude this case 3. Okay, I don't want that. I don't want that. So for that reason, I will choose what? So take b2 tilde is equal to really f. I will choose f. Then I will choose identity. At last entry, I will choose -1. Okay. So last entry, I will choose minus. For instance, this will also accommodate the 3-dimensional case. For instance, f -1. Okay. This will also accommodate this thing. So b2 tilde is really diagonal of f I2 cross 2, I2 cross 2. This is really -1. So now a b2 tilde is equal to b2 tilde a. So therefore I will get this. Actually there I was choosing 2f because 1f will also be sufficient to conclude that R alpha is equal to really identity or minus identity. Hence I will get this thing. A is equal to either the identity 1 or A is equal to really minus identity 0, 0, 1. Okay. And minus identity, this is a 2m cross 2m matrix. Both are so in both cases this belongs to SO 2m. But I have to exclude these cases. This is the second case. Okay. And what is the second case? This second case is really, this is everywhere, this is -1, -1, -1. The last entry is really 1. So this is second case is really everywhere, this is so this is really okay, minus identity 1. Let us not write this. So in the look just so what I have to exclude this case. Okay, so let C 2m 2m, 2m plus 1 be as in the case of SCU 2m plus 1. So what is this C2m, 2m plus 1? This is the if you remember, this is the matrix. If you really okay, so what is it? Suppose this is the matrix. If you take this thing, diagonal of mu1 mu2 mu1 mu2, this mu2m mu2m plus 1, and if you multiply this with C2m comma 2m plus 1 and C2m comma 2m plus 1 into this matrix, say mu1 mu2 up to let us write. So C2m comma 2m plus 1, and if you look at this matrix mu1 mu2 mu2m plus 1, so that if you apply this thing, then that will give you mu2m is equal to mu2m plus 1. This was the matrix C2m comma 2m plus 1. So and since this thing A has mu2m entry and mu2m plus 1 entry are different, one is -1 and one is 1, therefore A cannot commute with C2m comma C2m comma plus 1. Okay, since okay, let us write that. Since minus identity 0, 0, 1 into C2m comma 2m plus 1 not equal to minus identity, okay, not equal to minus identity 0 0 1 C2m comma 2m plus 1. This implies, okay, minus identity 0 1 cannot belong to center of SO2m plus 1, and hence center of SO2m plus 1 is equal to value identity. Manoj, that is clear?
Yes.
Okay, so let us do one more example. So now let us do it for sp2nr. Let G is equal to really sp2nr. So let A belongs to Z of sp2nr. So we have this embedding GLNR inside, sits inside really sp2nr. And what is the embedding here? I have discussed this thing when this we have proved that this is non-compact. This will go to like this thing u0 0 u transpose my inverse. This belongs to sp2nr. So let this thing u is equal to really diagonal of 2 3 up to n plus 1. So that means let b1 is equal to really u and 0 0. Since u is a diagonal matrix, this is really u inverse. And what is this thing? This is diagonal of 2 3 up to n plus 1. 1 by 2 1 by 3 up to 1 by n plus 1. So these are have different eigenvalues. Hence a b1 is equal to really b1a. That implies that a of ei is equal to really mu I ei. So I is equal to 1 to n. And a ei is equal to something like lambda I ei 1 I less than equal to n. I could have written 1 less than equal to I less than equal to 2n, but I am just renaming this mu n plus 1 to mu 2n by lambda I because I have some. This is really I from n plus 1 to 2n because okay. So hence a is equal to really diagonal of this thing mu 1 mu 2 mu n lambda 1 lambda 2 up to lambda n. Okay. Okay. Now what I have to show? I have to show this mu 1 is equal to mu 2 is equal to mu 3, mu n, something like mu n, and lambda 1, lambda 2, lambda n, everything is same. Let us first show this mu 1 equal to mu 2 is equal to mu n, and lambda 1 is equal to lambda 2 is equal to lambda n. Let us show that. So let okay b1 let b jk tilde, okay, bj jk tilde is equal to really, this is really bjk, okay, this bjk, okay, 0 bj comma k transpose, okay, okay, let bj comma k tilde is equal to bj comma k 0 0 bj comma k transpose inverse. By definition, this belongs to really sp2nr because of this thing u0 0 u inverse. Because of this u0 0 u transpose inverse belongs to sp2nr, where this bjk comma k is really as in the case of un. Remember this bjk comma k is the permutation matrix which really changes row j and row k. And if something commutes with bj comma k, if a diagonal matrix commutes with bj comma k, that means jth diagonal entry is equal to kth diagonal entry. That is the thing. But bj comma k is really transpose is equal to bj comma k. That is a symmetric matrix. And also bj comma k inverse is equal to really bj comma k. So hence bj comma k tilde is equal to really bj comma k 0 0 bj comma k, because now you will get this thing a bj comma k tilde is equal to bj comma k tilde a. So this is a really block matrix. It will multiply blockwise. So from if you really take thing this 1 less than equal to j not equal to k n. So if you really multiply blockwise, if you use this thing, then you will get this thing mu j is equal to mu k, and lambda is equal to lambda k. So this is really, hence a is of the part. This thing mu I 0 0 lambda I. Okay. Now I have to show this mu is equal to lambda. So let j is equal to really 0 I minus I 0. This is the complex standard complex structure on R2N. And the thing is this minus of j actually defines this sp2nr. I have also told you that this on some occasion I have told you that this j is belongs to really sp2nr. So that is also easy to see if you have forgotten that, because j square is equal to minus identity and j transpose is equal to really minus j. Hence if you look at this thing, hence this thing j transpose j j. Okay, so j transpose is equal to minus j and j into j. Use the fact that j square is equal to minus identity. So that means this is really j. Hence this j belongs to really sp2nr. Minus of j defines this group sp2nr. You have remembered this thing. Now a j is equal to really j. Sorry, I am 5. Okay, so okay. Just I will finish this thing. Okay, so now aj is equal to really j. This is really mu I 0 0 lambda I. This is really 0 I minus I 0. So 0 minus I 0, and this is mu I 0 0 lambda I, and this is really give you what 0 minus mu I lambda I, and this is 0. This is really 0 minus of lambda I. This is really mu I into lambda I. Mu I into 0. Mu I 0. Now look at this expression lambda I and mu I. So this implies lambda I is equal to mu I. This is really lambda is equal to mu. Hence A is equal to lambda I. Now as A belongs to sp2nr, this implies A transpose JA is equal to J. So now you put this thing A is equal to really lambda I transpose J lambda I is equal to J. So that means I transpose is equal to I. So this will give you lambda square J is equal to J. This is equal to lambda square is equal to 1. This implies lambda is equal to plus minus 1. Hence I will get what? Hence Z of sp2nr is equal to plus minus identity. Now similarly, Z of sp2nc. Okay, this is really 9th example. So 10th example. So for sp2nc, take the same matrices as that of as in this thing has been sp2nr case, and thus we get in this case that Z of sp2nc is really it's the same thing, plus minus identity. Okay, so I have really give you some example how to really calculate the center of some familiar matrix. So I will leave other things to as an exercise. You spend 10-15 minutes for each exercise. If you do not get, then just let me know, or otherwise what I will do, I will write this everything in detail, and I will send letter to all of you when this course is over. And so in the next lecture, actually we will compute one or two killing form, and I think in the next lecture I will really end this course. So, and let us see. Okay, the next lecture what you can do, but if there is any question, you can ask me now. Okay, Rajesh Bhaiya, you can stop the recording then.
Okay. Yeah.
Thank you.